So this lesson is another discussion on continuity. So let's remember our naive notion: a function is continuous if there's no breaks. It's not continuous if there is a hole of some sort, if there is a gap of some sort, if there is an asymptote of some sort. Those are various types of discontinuities that we've looked at earlier. Now, what's our formal definition of being continuous? What do we say? A function f is continuous at a point C. There's C. There's the function f. It is continuous at C if the limit exists. We're calling it equal to L. So the limit exists. The value of the function exists, and it equals L. So that's our formal definition of continuity, but we want to add some things to that, some concepts that we can talk about. And the first notion is that of polynomials. So remember what a polynomial is. I'll give you an example of a third degree polynomial. F of x is ax cubed plus b x squared plus cx plus d, various powers of x, descending powers of x, all positive numbers, 3, 2, 1, and then, of course, x to the 0 in a sense. A, b, c, and d are real numbers. Polynomials are continuous everywhere. So let's take a look at a graph. If I just pick a polynomial like this, f of x is 2x cubed minus 4x squared plus 3x plus 5. It's supposed to be a cube. That's a polynomial. There are no breaks. There are no breaks anywhere. I can change it up. Notice still no breaks. I could add a higher power. Now we're at x to the 4th. And change that up a little bit and see what we can do to change it. Again, no breaks. Polynomials are continuous everywhere. So there are no points of discontinuity. Now let's talk about rational functions. A rational function g of x is of the form p of x over q of x, where p of x and q of x are both polynomials. Hopefully my dog's not snoring too loud. So here we go. P of x and q of x are both polynomials. Now, are they continuous everywhere? Let's take a look at a fairly straightforward example. Polynomial on the top, polynomial on the bottom. So let me just call it g to be consistent with the other page. So I'm going to say x squared plus 3x plus 3x minus 4. That is a polynomial divided by x minus 2. And you will notice something is happening at 2. It's broken. It's in 2 pieces. We can see that. And we have what? We have an asymptote at x equals 2. You can draw that in there. And you'll notice 2 is not in the domain. 2 is not in the domain of this function because that would make a 0 downstairs. And that's not acceptable. So indeed, there is a break. These are in 2 separate pieces. And we could say this function is not continuous at x equals 2. But what do we say here? Rational functions are continuous everywhere on their domain. So those are a couple things for us to think about. So we look at another example of a rational function. If I say, for example, r of x, we'll put an x minus 3 downstairs, so right away we know, oh, that could be a problem. How about x squared minus 5x plus 6? We would argue, no, 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 3 is not in the domain, so r of x is not continuous at 3. But it is continuous everywhere else. So in terms of listing a number line where that thing is continuous, we remove 3, but everything to the left is continuous, everything to the right is continuous. And then we would say interval notation negative infinity to 3 union 3, 2 plus infinity. But let's take a look at this graph and see what's happening. Can we see that that's not in the domain by looking at Desmos? So let's clear what's there. And we're calling it r of x this time, rational function. R of x is upstairs x squared minus 5x plus 6. Divided by x minus 3. And it looks continuous. It looks continuous, is it? What's happening when I get to 3? When I get to 3, you'll notice it says it's undefined. So despite the fact that the graph doesn't tell us, there's actually a hole there. So I will emphasize that fact. 3, 0 actually has a hole. Excuse me, not 3, 0, but 3, 1. Again, as we get very, very close to 3, it tells us that that's undefined. So 3, 1 is actually a hole. Now, no asymptote, that might get you thinking a little bit, but the reality is the numerator can be factored. So just to kind of show you what's happening there. We have x squared minus 5x plus 6, x squared here, plus 6 here, minus 5x there. How do we build x squared? X times x. How do we build 6? How about negative 3 times negative 2? So negative 3x and negative 2x add up to negative 5x. So we get x minus 3, x minus 2. And you see, in an essence, the x minus 3 divides out, but not completely. So it's x minus 3 times x minus 2 divided by x minus 3. So in a sense, it behaves kind of like x minus 2. I'm going to write equals, but recognize that 3 is not in the domain. So the graph is like x minus 2 just by removing 3. And you can recognize that is exactly what we said here. It behaves like x minus 2. 3 minus 2 is 1, just removing 3. But again, the key idea is a rational function is continuous everywhere on its domain. So all you've got to do is restrict that value, remove that 3, and it's continuous everywhere else. But the interesting problems become the piecewise functions. So let's take a look. F of x is 3x plus 1 if x doesn't equal 2, and it equals 5 if x equals 2. So looking at that graph, we'll try to do it on Desmos. I don't think Desmos can handle the not equal. We'll try it. We know it is 3x plus 1. But we are supposed to remove the value at 2. The value at 2 looks like it should have been 7. We'll remove that. So 2, 7 will make a hole. So that is not there, but at 2, the value is 5. And then the question is this continuous? First off, it does pass the vertical line test. Notice a vertical line only hits it in one point. However, there's a gap. It is a removable discontinuity, but what's our issue here? What is our issue? Well, let's take a look. What do we need to know? What are the facts that we need to have to prove that something has a limit? Remember, the limit has to exist, the function has to exist, and they have to be the same. So for this question, does the limit exist? Well, let's look at it. What is the limit as x approaches 2 from the left? Limit as x approaches 2 from the left of f of x. Let's go back and look at our picture. As I approach 2 from the left, where are the y values headed? They're getting closer and closer to what? Closer and closer to 7. Similarly, as I approach 2 from the right, the y values are doing something similar, just to visualize it. I approach 2 from the right. X values are approaching 2 from the right. Y values getting closer and closer again to 7. So therefore, the limit exists, and it equals that common value. So the limit as x approaches 2 of f of x equals 7, but f of 2 equals 5. They're not the same. So f is not continuous at 2. But what about the rest of the numbers? Well, away from 2, it's 3x plus 1, and 3x plus 1 is a polynomial. So away from 2, it behaves like a polynomial. So away from 2, it's continuous everywhere. So f is continuous everywhere except 2. So we remove 2, we shade either side. We get negative infinity to 2 union 2 plus infinity. That's where it's continuous. So the breakpoint in a piecewise function is always going to be a place for us to examine, because that's going to behave a little differently than other sorts of things. All right. What can we look at next? How about something like this? G of x equals x squared if x is less than 3. It equals 2x plus 1 if x is greater than or equal to 3. And again, let's try to take a look at it and see how it behaves. So the first part of this, we have x squared if x is less than 3. And I want to emphasize that this is one function, even though I'm drawing it multiple ways, this is one function. And it is 2x plus 1 if x is greater than or equal to 3. And if x is 3, we use 2x plus 1. 2 times 3 is 6 plus 1 is 7. So therefore, this point 37 is a solid dot. And this point, as we get close to 3, this point 39 would be an open dot. So you would say this is right continuous, but not left continuous from this picture. So that's what we have. And we can see the thing is not continuous at 3, but why? But why? How do we answer that? What are we going to say? Well, we're going to look at the limit. What is the limit as x approaches 3 from the left? Choose numbers close to 3, 2.9, 2.99, 2.999. We're all on this branch a little bit to the left. A number a little less than 3 squared is a little less than 9. So we're approaching 9 from the left. And we can see that on the graph. Approaching from the left, Where are the y values headed? Getting closer and closer and closer to 9. Approaching from the right, we are on this branch, 3.1, 3.01, 3.001. Limit as x approaches 3 from the right of g of x. Numbers close to 3, a little more than 3 times 2 is a little more than 6 plus 1 is a little more than 7. Is getting closer and closer to 7. So the limit does not exist. If the left-hand limit does not equal the right-hand limit, the limit does not exist. So what is our conclusion? G is not continuous at 3. But again, away from 3, to the left of 3, x squared behaves like a polynomial. To the right of 3, 2x plus 1 behaves like a polynomial. So it's continuous everywhere else. G is continuous everywhere but 3. So again, 3 gets removed, and we say where it's continuous. It's continuous on this interval, which is minus infinity to 3 union 3 to infinity. And then looking at our graph, that sure looks like what we saw on our graph, right? Continuous everywhere to the left of 3, continuous everywhere to the right of 3. But at that breakpoint, crazy things start happening. So that's something for us to look at. But there are other kinds of situations we could have with breakpoints. What if I have k of x is 2x if x is less than or equal to 3, but it's equal to x plus 3 if x is greater than 3. First off, what's k of 3? K of 3 is on this branch, 2 times 3, which is 6. How about the limit as I approach 3 from the left? Limit as x approaches 3 from the left of k of x. 2.9, 2.99, 2.999, getting very close to 3. We're on this branch. 2 times very, very close to 3 is very, very close to 6. How about this branch? Limit as x approaches 3 from the right. 3.1, 3.01, 3.001, a number very, very close to 3 plus 3 is a number very, very close to 6. So thinking through this, we believe the limit as x approaches 3 of k of x equals 6. We said k of 3 equals 6. Therefore, k is continuous at 3 at the breakpoint. Now, to the left of 3, it's a polynomial. To the right of 3, it's a polynomial. So therefore, it's continuous away from 3 as well. So k is continuous everywhere. So we were able to do that analysis without looking at a graph, but let's quickly look at a graph now. So we're going to start with k of x is 2x if k is less than or equal to 3. And just for emphasis, if k is 3, 2 times 3 is 6, I'm going to put the 0.36 on the graph. So 3,6 is a solid dot. And then the other one is k of x is x plus 3. The other part of this, again, one function, not two. K of x is x plus 3 if x is greater than 3. Does that function look continuous to you? It sure looks continuous to me. We can draw it without lifting our pencil. There's no hole. There is no gap. So that's a nice situation. All right. What about a situation like this? What if I have k of x equals x plus 1 if x is less than 4. It equals 2x if x is greater than 4. Do I've got to think about this much? It's certainly continuous to the left of 4. It's certainly continuous to the right of 4 because those are both polynomials. But what's happening at 4? Do I need to look at the limit? The answer is no. Even though the limit does not exist, the limit will be different. But I don't have to do that because I recognize 4 is not in the domain of K. Four is not in the domain. It's defined less than 4. It's defined greater than 4. It is never defined at 4. So K is not continuous at 4. Even if I had made the limit be the same, which I can do, I'll make a similar kind of case. If I go g of x is x plus 3 when x is less than or equal to, excuse me, x is less than 2. So it's x plus 3 if x is less than 2, so it's heading to 5. And it equals 2x plus 1 if x is greater than 2. So that's also heading to 5. So the limit exists, right? The limit as x approaches 2 of g of x will indeed be 5. But again, 2 is not in the domain. That's less than, that's greater than. There's no value. 2 is not in the domain of g. So g is not continuous at 2. Just to remind you, as we finish this off, we have to think about these rational functions though, right? So we'll just quickly do one more of those. If I have r of x equals x squared minus 4 downstairs, and who knows whatever's happening upstairs, x cubed plus 3x plus 1. The bottom can factor into x minus 2x plus 2. Whether it divides out of the top or not, I don't think it does, but it doesn't matter, frankly. The rational function is continuous everywhere in its domain, so it cannot be continuous at 2, it cannot be continuous at negative 2. But it is continuous everywhere else. So if I would lay out my number line, remove negative 2, remove 2, continuous everywhere else. Negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. That's where it will be continuous.